Hey, Robert.
Dr. Terrell, I sent you an email earlier because my Wi-Fi wasn't working, because SJSU email is, sorry, SJSU Wi-Fi was not working. So I had a question about the Excel file. Can you hear me? No? You're muted. Dr. Terrell, you're muted.
Okay, thank you. I'm going to remute it.
So can I share my screen real quick? Is that okay?
No, Kenya, you can.
I just want to show you what I got.
Okay. Just 1 sec. Just 1 second. 1 second. 1 second. I'll be right back. Okay.
Oh, where's my Excel?
What'd you get, Calvin?
Huh?
What'd you get?
Where?
Dude, I'm like, I don't know.
Because I don't know if he wants the definition or he wants the data. I was like, this is like the Y set data. I'm gonna ask him about that.
Okay, let me see if I can figure out how to let you share your screen. I don't even know how to use this.
Oh, so just go on the little green button that says share screen, and then there should be like a little triangle like this, and then you can click it, and then it'll say that allow others or something to share screen.
AK Advanced Files Basic. You are screen sharing. Participants. New share, pause share, annotate, remote control, more. Live, open computer center, optimize share. I can't find it, man.
So you can put you have to stop sharing your screen so that you can change the setting.
All right, I'm going to stop sharing my screen. So you are screen sharing. Stop share. Okay, I'm not sharing.
Okay, and then at the bottom where the green button is that says share screen, just hover over it, and then there should be like a little triangle like this on the corner.
Okay. Okay.
And it's going to say something like allow others to share or something like that.
I think you can make like a co-host too. That might work better.
I can make a co-host. Jesus. I'm like a stupid 7-year-old here. I don't know what I'm doing.
It's okay. So Dr. Terrell, my main question was on the residuals and the R squared. So I just want to confirm, is the R squared residual squared or is it something else? I just want to make
sure. It's a sum of the squared residuals, yeah. So I'm sorry.
So that's chi-squared.
Chi-squared, right? Sorry.
Chi-squared is the sum of the squared residuals. So then R squared is residual squared.
Right.
Okay. All right, awesome. I just wanted to
Good.
double check because
Yeah.
I finished it and I wasn't sure like 100%. I was like, yeah. So then,
Okay.
yeah, if we have residuals that are like perfect, it means that it matches the mixture.
It matches the Linest.
The Linest. Okay.
Yeah, the Linest has the R squared. It's on the right side near the bottom. Is the chi-squared. Or it's actually,
Yes.
it's technically, it's not chi-squared. It's this sum of the squared residuals. Chi-squared is that divided by the degrees of freedom.
Okay, so then chi-squared would be the sum and then divided by degrees of freedom?
Yeah. But you don't have to worry about chi-squared. Just take your sum of squared residuals. You compare it to Linest. And it should be a little bit larger than the Linest one. And it'll be a large number because you've got gazillions of points.
Yeah, the one on Linest is like 206, 9, 103, and then mine is like 104. So,
Wow, that's awfully good.
okay, it's like 103.9 and mine is 104, but you know,
Oh, okay. All right.
yeah,
Perfect.
just making sure.
Perfect. Okay. Oh, goodness gracious. Oh, you're welcome. Welcome. So now I got to figure out how to share a screen again. Oh, there we go. Share a screen. Screen the tool. Okay. I gotta figure out what I'm doing here. There we go. Here's our backscatter interferometry paper, right? Turns out this guy, Robert Dunn, is he's from Kansas. And just publishing these damn papers all by himself. I guess he has a student working with him there, you know. And then I've got this paper for us to look at. There's the one we've got now. The near field scanning optical microscopy is it's a kind of a weird thing, actually. It was big in the 90s, but it sort of has gone away. People are like, it's a lot of work to get what you get. So let's see here. I wanted to get a picture of Robert Dunn. Who are we dealing with here? Robert Dunn, Kansas. Primary chemistry. Oh, he's the chair. Oh my God. Poor bastard. Oh, come on now. Okay, hold on. Oh, here, let me show my students. My son has made his morning coffee. Oops, I have to hold it in front of my face. Otherwise it vanishes. This is espresso. What type is this, Robert?
Ethiopian.
Oh, this is Ethiopian Harar. It's a special type of bean that they don't take the cherry off completely or something, and they ferment it with the cherry on it. And apparently that makes the coffee really gross, except if you're Ethiopian, in which case it makes it really good. Okay, there's the Dunn. Oh, there he is. There he is. The Dunn group. Are you done yet? Okay. So I can't get to anything because it's stupid. There he is. I know this guy. I've met this guy. He went to Sac State. Holy crap. He got his PhD at UCSD. Oh my God. Now he's in Kansas. That is like being in hell because it is so boring in Kansas. I mean, if you want to have a great career, then definitely go to Kansas because there's nothing else to do. It's like frozen tundra most of the year. and then it alternates between frozen tundra and like raining and hotter than hell for like 4 or 5 months, and then it goes back to frozen tundra. And it's not even pretty tundra. It's like wind blowing, all this agribusiness. It's huge, you know. So you just stay in your stupid building and pretend that you're having a good time, I guess. So there's Robert Dunn. I know this guy. I do know this guy. Let me see if there's another woman I knew from Kansas. I think she was postdocing there. Or thought maybe she got a faculty position there, but I don't see her there. Okay. Enough messing around. Now he's looking older. Looks older there. Kansas will probably do that to you. Let's see. All right. So I wanted to talk a little bit about backscatter interferometry today because it's the detection method used in this capillary, right? And you'll notice that, you know, it's a very small capillary, right? And somehow he gets this signal out of it, right? And the signals are weird because some of the peaks go up and some of the peaks go down, right? And so what backscatter interferometry is doing is it's measuring the refractive index in the capillary. And Mr. Dunn, Dr. Dunn here, he's got a fancy-dancy thing where he his interferometer modulates the wavelength. I should probably describe the stupid thing first. Let me get the paper. That's not it. Here we go. Okay, so here's a picture of the backscattering interferometer. It's really simple. He just has a laser and a beam splitter. You know, the laser focuses in the cavity, in the fiber. You know, the little tube where the liquid's coming through. And then the same wavelength bounces back out and then recombines. There's basically two reflections. There's a reflection off the top surface and the bottom surface of the capillary. And there's a little bit of light that goes through the liquid. And those two beams recombine, and then they create an interference pattern on a little detector out here. And they actually use a split photodiode when they're doing the actual work there. So let me see if I can give you a better picture there. So this is a slightly different. Oops, this is not the right one. Here it is. This is a little bit better description of it. This uses porous silicon, right? But the idea is the same. In this, what I'm showing you here, and what the backscattering interferometry is. You have a source of light coming in, and it reflects off the top surface, and then a portion of the beam goes through the liquid in the capillary, bounces off the back of the wall, then comes back out. And this beam recombines with the top surface reflection into the spectrometer. Okay. This is 1,160. I'm going to find this guy. Okay, so here's what happens. As you change the refractive index in the capillary, the spectrometer sees this changing pattern of interference fringes. And I'll put this on the web for you guys to see, for y'all to play with it. But it's a simple thing, right? But you can see that there's a couple things happening. The phase of the fringes is drifting left, higher frequency, and the frequency of the fringes is increasing as the refractive index increases, right? So this weird envelope here encodes the thickness and refractive index of this medium in here, this medium that the beam is reflecting off of. Okay, somebody ask a question. Please.
What is a fringe?
These peaks in the reflection are called fringes. So like normally they would be, it's all historical stuff. Like if you develop this on a plate, on a piece of film or something, then it would be a series of vertical lines, and this would be the most intense line. This would be a weak, this would be second most, third most, fourth, fifth, sixth, seventh. This would be a series of lines at different intensities. And for some reason, they're called fringes. I don't know. Okay, someone else ask a question. Calvin.
I have a question.
Okay, what am I talking about then? You have no idea what I'm talking about, but you don't have a question, right?
Yeah.
Yeah? Damn it. What am I to do? Dan, do you have a question?
I have a question.
Yes, Carla. Thank you. I can't hear you.
Hello? Does that
Yeah,
work
I
now?
can hear you.
Okay.
Yeah, I can hear you.
Cool.
Now.
How does the spectrometer go from the image to the graph? Like, I'm not quite sure I understand how it does that.
Yeah. So this is not an image at all. This just is shoving all the light together and dispersing it across a grating by wavelength. Basically, this is a rainbow, and this is the intensity of the light across the rainbow from blue to red, See, that's a good question. I like that question. Oh, I'm so cranky today. So cranky.
Dr. Taylor,
Yes, Richard.
is it a double rainbow?
No, it's not a double rainbow. It's not a double rainbow. In fact, there are filters in place so that you do not see any second order diffraction. That is.
Can I ask a question?
No, someone else. I'm just kidding. I'm
So
sorry.
my question is,
Yes.
so we're going from the source to the
Yeah.
spectrometer.
Yeah. hmm
Is the spectrometer the one that's measuring RI, or are they using like a different instrument for that?
Yeah. So the spectrometer has a grating and a detector in it. You know, it has you know, it's actually a Cherny-Turner type spectrometer, which we studied in Chem 155, which no one remembers. Right, Calvin? Calvin, he won't even comment.
Yes,
Yes. Yes, you do, or yes, you don't remember.
a little bit, but
Okay, all right. So in the light comes into the spectrometer and it bounces off a couple of mirrors, and then it bounces off a grating, and then it's all separated by wavelength. And the rainbow shines on an array detector, and the array detector, you know, each pixel in the array is represented here, you know, in this frequency spectrum. Yeah. So the spectrometer has both the wavelength separation and the detector all in one. And it's an array detector, so it sees everything all the time.
So on that graph, that blue dotted line, does that represent like the maximum frequency at that frequency?
Yeah.
Or
Yeah,
at
this
that
is
time?
right. So, you know, I was getting fancy there, right? Because this is actually a black body spectrum. And because I use a quartz tungsten halogen lamp, and it's just a black body radiator. Does that make sense? So in physics, they talk about black body radiation, and there's no undergraduate physics course worth its salt that doesn't at some point in time describe black body radiation. And it's probably some weird physicist type who makes it completely impossible to understand. But basically, if you heat something up, it glows, right? If you heat up a stove, you know, it gets red hot, and eventually, you know, it'll get white hot, you know? And so the spectrum of light that comes off that heated body is called a black body spectrum. And so in an old-fashioned light bulb, like I use here, it's a heated tungsten coil, and it gives off a black body spectrum. And it's kind of predictable. So I just made this the intensity profile for the lamp, right? And then I modified that with the Fabry-Perot refraction equation, and then it came out like that. So I like these questions. That's good. I think Carla gets an A today. And Kenya. But I don't know if anybody else is going to get an A. I still have to be convinced. Calvin definitely does not get an A because he couldn't remember that well. All right. So this is called a Fabry-Perot interferometer, right? And it's called Fabry-Perot because everybody wants to get their goddamn name on an optical instrument, right? It's the same as a backscatter interferometer. It's the same goddamn thing, right? Just Fabry-Perot, you know, they did it in 1700 or something, you know. They looked at soap bubble films or something, you know. And if you reflect light off a soap bubble film, you know how they look kind of green and purple and red and stuff? They give this iridescence. That's this effect. That's Fabry-Perot interference. And if you had a little spectrometer to look at that light, it would be wiggly like this, right? And the wavelength and the thickness and the refractive index they're all wound up in here, right? So in this case, what I did was I took the data off of this is the point value in a spectrometer. It's kind of like the wave number, you know. And you can actually, but actually, I think I take these point values and I convert them to wave numbers, right? The point value has a wavelength, and I convert the wavelength to wave number. And then I Fourier transform it. And this whole blobbity blobbity blob thing here turns into a single peak. This blob turns into this green blob. Now, who knows anything about the Fourier transform?
They use it in mass spec.
They do. They also use it in NMR. And low budget people, such as myself, use it in spectrometers. You can use it in FTIR, Fourier transform infrared. Yeah, and this is simple. This is backscattering, and we Fourier transform the data. And what you do is, if you have a sinusoidal signal, right, and you Fourier transform it, you get a single line, right? Because think about it this way, right? If you've got a sinusoid, that's just equivalent to a single sinusoid, right? So you can convert that sinusoid between these. It's called the Fourier domain and the time domain. And in the time domain, if you have a signal going up and down, and you Fourier transform it, you get one thing. If you have two things going in, you'll get two things. And if you've got a whole spectrum of things, you'll get a whole spectrum of things in the Fourier domain. But this signal up here is really simple in the Fourier domain. I mean, it's not trivial because, you know, it peters out on either end, and it's got this envelope, right? And it's probably not completely uniform, but it's got one main frequency component, right? It's got, if you count the distance between the peaks, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, right? Then you can get the frequency of that sinusoid, and that is what's plotted here.
So that's the green line that we see, or?
Yes. Yeah, the green line is the Fourier transform of this black line up here.
So, Dr. Terrell,
Yeah.
on the graph with all the little,
This one?
yeah, that one. How do you know when to stop counting, like the peaks? Because on the very right side, there's such like a small, but it's like a tiny little one. So how do you know
this little blob out here? Okay. So what you do is you throw the whole mess into the computer, into the Fourier routine. And then the Fourier routine just spits back the coefficients, right? And, you know, you don't really have to care about that at all, right? I mean, there's, let's analyze this for a second, right? Every point in this domain corresponds to a point in this domain, right? And so, you'll notice that this starts around 200 and ends around 200. Right? And so what this means is that there's a zero frequency offset of about 200 counts. So if we follow this green line up here, it's going to shoot up to about 200. Right? That's one thing that you can know about the Fourier transform is this is elevated off of zero by a couple hundred points. So the DC component or the zero frequency component will be up around 200. And then the low frequencies come down and they quickly go to zero, and then you get a bump, right? This is zero frequencies like DC, and then you get a bump, and then it goes back down to zero, right? So if we go up to the higher frequencies, that's corresponding to point to point to point to point. There's really not a lot of really high frequencies in this. So these are all down around zero, right? But we get a good 50 points here to define the average frequency of this bunch of blobs.
So then is the frequency the y-axis on the second graph?
So this is the amplitude versus, well, okay. So let me lie to you for a little bit longer, and then I'm going to tell you the truth, okay? Fourier transform is normally defined in the time frequency domain, right? So this is, the domain is the x-axis, right? So if this is the time domain here, we've got a bunch of peaks. This looks like sine of omega t, right? Right? It's wiggling, right? This could be a photon. You know, got a little spread in frequency. It starts, you know, and then it wiggles and then it peters out, you know? Now, if you Fourier transform that, you get a single broad peak, right? And the wave number here turns into centimeters here. So the frequency turns into, so the time turns into frequency, or the wave numbers turns into centimeters. Because the reciprocal centimeters is frequency in the optical world, and centimeters is centimeters. So centimeters, I don't know. It's the opposite. It's so reciprocal centimeters transforms to centimeters. Just take 1 over that axis. So you can go from time to frequency or reciprocal centimeters to regular centimeters. And this axis here is now called optical thickness. Optical thickness is refractive index times thickness. So it's just, it's just because the light takes longer to get through the higher index medium, you know? So more waves, I don't know, whatever. You know what I mean? The waves are shorter, so they come out and, they add up differently. They do this. They come in, they come out. And the optical thickness here is 2 eta L. right? And so 2a to L, the 2a to L value for this peak, we just take the weighted average of the the optical thickness in this peak, and then we can plot that versus time. And then that tells us the refractive index. And this is what the backscatter interferometer on the CE apparatus does. But this is a much more sophisticated version of it. Because what they do with the backscatter interferometer is they just use basically, it's almost like they just use two wavelengths and they oscillate between them. And so they kind of go, oh, if they're lucky, they're going up and down the side of one of these things. Okay, somebody asked me another question. Dan, you're very quiet.
What is this useful for?
Getting grant money. You have to be able to impress the people you're talking to, right? And if you know just enough to be dangerous, you can sort of like, and then you can get more grant money. So this is, and what this thing is an optical sensor, you know? And basically it's just like a real simple refractive index sensor. And it's a way to take this porosilicon, bounce light off it, and tell, oh my gosh, something's in the air, right? And then for the CE, it's a way to bounce light through the capillary and say, oh my gosh, something just eluded, you know? Something just went past the detector. And then
Thanks,
they
that
give
answered
you,
it.
and then they give you money, hopefully, if you didn't, if you're more, if you're better at it than I am. Okay, so
Oh, I
this is
have a
bad.
quick question.
Yes, please.
So then, the point value, that's
Yeah.
like, how is that time?
Okay, so time to frequency, or inverse centimeters to centimeters, right? So actually, this point value actually, I cheated, right? Because the guys at UCSD that did this work that I was sort of copying, they just take the readout from the CCD just in numbers, just point numbers. They dump it into their Fourier routine and they Fourier transform it. They get back a meaningless number here. But what I did was I took the data back from the spectrometer, and then I had the wavelengths assigned to the points, and then I replotted it as amplitude versus wave number, which actually reverses the whole thing. The highest point is the lowest wave number, et cetera, right? And then I Fourier transform that. Oops. Then I Fourier transform that, and then I got this. Because if you do that, it actually transforms into optical thickness. Thickness times refractive index. So who here has seen a graphic equalizer on a stereo system? Okay, you guys. this. Well, let's look at videos. Well, here's a graphic equalizer, right? This is like, they have all these knobs, you know, and you can change these are the high frequencies, these are the mid-range, these are the low frequencies. And you can adjust the volume in each channel, right? Does anybody know what this is talking about? Is this helpful to anyone?
I've seen this, but I did not know that it was called a graphic equalizer.
Excellent, excellent, excellent. There's one. Let's see here. Yeah, here's one right here. Let's look at. See how there's this bar graph here, and this shows the gain at different frequencies. Low, they got the bass turned up, the mid range is turned down a little bit, the high frequencies turned up, you know. And then if you got a ton of channels, you can show a ton of different frequencies or whatever. And this is just the Fourier transform of a byte of sound. You know, so if you got a really pure tone in there, you'll get a spike in this. You know, obviously, in this case, you've got some bass, some mids, the trebles are falling off here a little bit, you know. But this is the same thing as a Fourier transform. This is a Fourier transform. This just Fourier transforms the sound. Sound is intensity versus time, or pressure versus time, air pressure versus time. And this is air pressure versus frequency, so 1 over time. Time, and then time is seconds, and then per second is frequency. So I'm just sort of trying to demystify this stupid thing a little bit, you know, right here, right? So you just take this in your Fourier transform and you find the major frequency component in here. And because you know how it works, right? It sort of, it accordions like this as the refractive index changes. As it accordions, the frequency increases. Like say the refractive index goes up, then the frequency component in here will increase, right? And then this peak will move to the right, I guess. You know, as with increasing refractive index. You know, and so like if you have ethanol vapor and dry air, you can cycle it past, you know, a piece of porous silicon, right? It's like a soap bubble film, and you can watch it absorb the gases in that way. So this is what Dunn is doing, but he just has a very narrow wavelength range, and he's got it. It's a weird tunable laser. It's a little tunable cavity. You can just make this small change. You know, it probably goes from like 650 to 640, 650 to 640, and it just sort of bounces back between those two wavelengths. And then that creates a little dancing pattern here. And then he puts this onto a split photodiode, probably right around there, you know, right around the transition. And then he can pick up the changes in refractive index in the capillary in this optical image here. And then he plots that versus time. And then that gives him his electropherogram. Okay, somebody paraphrase what I just said. Aditya.
So his laser, he can, I guess, oscillate between, you said 640 and 650,
Yeah.
which then goes through the
This is
mirror?
the this is
No.
a beam. This is a beam splitter, and it's so there's a part of the beam that dumps out there, but there's a part that goes through and reflects off the two sides of the capillary, and comes, and then it goes over here, and that hits a detector.
I kind of got lost there.
Okay, so there's the laser comes in here, goes through the beam splitter, hits the capillary, comes up, and then hits the detector over here. So it goes through, back up, and then hits the detector. Through, back up, and over to the right. Over to the right. And it makes an image there, which is, if you take a cut through this image, that'll be like a couple of wiggles from the larger interferogram that I was showing you. Or this might just be like one wiggle, you know? It could be just like going up and down the side of one of the wiggles.
So I still don't understand why we would need like the FFT of the data that comes out of this.
Okay, so in this case, we don't actually Fourier transform it, right? What this tells us is the change in the refractive index will shift the intensity around in this image, right? This, I mean, it's, you know, because this is light going through the capillary, coming back, bouncing off this here, and then they don't actually even image it. They just put it on. It's called a split photodiode. It's just two detectors. And what they do is that they get the buffer flowing, everything, and then they zero out the detector. They zero the gain on either side of this thing so that it's reads zero. Then when anything goes by, it creates a big blip on the detector. It can be positive or negative. And that's just by change. And all they do is they look at the difference in intensity on either side of the detector. And then that is what they plot out on the screen. Does that make sense?
A little bit more, yeah.
Okay. Yeah. I mean, it's a little hard to get it all right. But the thing is that because of the way the light interacts in the capillary here, the reflection encodes the refractive index of the stuff going through the capillary. And this reflection just has like a sensitive kind of quality to it, right? And if you put that image onto a split photodiode just right, then you can see the refractive index translate into relative intensities on either side. And then that is what you plot up on your computer. And that gives you your electropherogram, rather.
So that would be something that you would have to do manually, like the setup won't do it for you?
Yeah, exactly. So these guys, they actually said that this is actually a 75 micron capillary, and this is not a super thin one, right? There's this thin wall capillary here, and I'm not sure, I think this one takes a half an hour to change the capillary and realign the optics. This guy here, probably it's really comparable, you know, but, you know, you have to, the capillary might be fairly short, you know, but, oh, by the way, this is the injection end and this is the detection end, right? So the analytes flow from the positive to the negative side there, right? That's it. Yeah. So the analytes are injected here, and then the electroosmotic flow goes this way, and then you detect right before this is like the waste, and this is the running buffer, right? And so then the analytes flow through this capillary and separate out, and then one by one, they go through this detection zone, and blip, 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 you get the peaks, and then they go to waste.
So, quick question, Dr. Taro.
Yeah.
Where does the Fourier transformer come into play?
Okay, so in this case, there's no formal Fourier transform is done. Let me see if I can illustrate here, right? So what's going on in that one is that it's like 650 nanometers, right? So it's like right up here. And if they're lucky, they're on the side of one of these peaks. If they're on the peak, then they're screwed, right? If all the wavelength and all the capillary thickness, refractive index makes them on a peak here, then they're not going to see any. They're going to have zero sensitivity. But if they're lucky, then they'll be on the side. Then as an analyte flows through, what will happen is it will go rip,
Oh, and then they use that to deconvolute the data and get the...
Right. Except in this one, they only see the rip, not the rip, right? It's only one part of that. It's only one part of a fringe. You know, it's only a fraction of a fringe that ever makes it, because they're basically going for super high sensitivity. You know, so it just shifts ever so slightly. It never goes over a whole peak. You know, it just changes ever so slightly.
Okay.
Okay, quick segue. The LIGO interferometer. Who here's heard of it? Oh, come on. Only Dan? No one else has heard of LIGO? Gravitational waves? The whole entirely new spectrum that we just found? Okay, all right. So it turns out, you want to explain it, Dan, or do you want me to explain it?
I mean, I don't know. The reason I know about it is I lived up in Washington in near Hanford. Well, not near, but Hanford's in Washington as well, and that's where the LIGO Observatory is.
Yeah. One of the LIGOs in Washington, the other one's in Louisiana, and then there's one in Italy, right?
Yeah, I knew there's another couple. I thought there was one in China, but maybe I was wrong.
They're building one in Japan.
Okay. Yeah, I don't know exactly the structure. I do know the it's a basic interferometer setup where you have one laser and then a moving beam, so that as you move the frequency, you match the frequency of the wave coming in.
Mm-hmm.
But all I got from that is that it's really sensitive, able to test a gravitational wave. I don't know.
Right, exactly. It's ultra sensitive. It is bloody sensitive. And that's what these guys... Yeah.
They got lucky, right? They were just kind of sitting around waiting, and then all of a sudden they were like, oh.
Right. They practically, they turned it on, and like that very same night, boom, they got a signal. They're like, no, they can't be real, you know? And they sat on it for a long time, thinking, this can't be real, this can't be real, this can't be real, you know? Because they had all these weird, the false positive things going on. Like they had fake signal injectors. So that, you know, and if only one of the detectors sees it, it's not counted, right? It has to go through Washington and Louisiana, both of them. They have to go at the same, they're like a couple milliseconds apart, because that's how long it takes the gravitational wave to move through the Earth. You know? It travels at the speed of light. Boom. So to get from Louisiana to Washington State takes a few milliseconds, right? And you can describe them as not Fabry-Perot, but these are Michelson interferometers. And the Michelson interferometer here is basically you've got a source of light, you've got a beam splitter, and then you've got a mirror, a detector, and then a second mirror out here, which let's just say that maybe this mirror can move, right? So shit, you know, I fucked that up. Sorry. It's a light source, beam splitter. And then there's the detector down here. You got two mirrors. And then basically, fuck, I fucked it up again. That's amazing. Light source. And you've got a couple of paths there. And they combine going to the detector, right? You've got light coming in, and then this is a beam splitter here. Oh wait, you guys can't see that. It's all out of focus, sorry. Now it's less out of focus. Okay, good. So you've got the light coming in, that's a laser beam, right? Then it hits this beam splitter, and then part of it goes through and comes back and then goes to the detector. And part of it bounces, comes back and goes to the detector. And these two beams, when they recombine, they can tell you about the difference in path length getting to this mirror and this mirror. Okay, so the difference in the path, it's called 2a minus 2b is equal to n lambda. And so when n is an integer, then you'll get a peak. And when n is a half integer, you get a dark signal at the detector, right? And so this Michelson interferometer. And so in this case, what they're looking for is differences in the arm length, A and B. And they're using what they just use the overall intensity. They look at the intensity at the detector, right? Because as you go through 2a minus 2b, what you'll see is that this is the path length difference here, right? You'll see a sinusoidal pattern like that, right? Where this is the intensity. Actually, you see a cosine squared pattern, whatever. But what they do is they just park it at a certain place here. At a place like this, and they look up for the change intensities. And they can see delta with a noise on the order of 10 to the minus 12 meters. And A and B are both a couple of kilometers long. So it's like, you know, it's a fraction of the width of a proton, not a hydrogen atom. It's like a thousandth of the diameter of a hydrogen atom. And then you get down to the little nugget in the middle, right? So this is the interferometer as a high resolution length detector. And how did they do that? Well, I don't know. They manage somehow, right? They use a megawatt of laser power, et cetera, right? In the backscatter interferometer, in this guy, what they do is that they detect 700 micrograms per liter in a volume of 90 picoliters, right? This is their high resolution, right? This is a change in refractive index, right? Because the interferometer changes with the optical thickness, which is refractive index times distance. So so this backscatter type detector is pretty cool, pretty sensitive. But what they found was that it actually had a similar sensitivity to an ultraviolet absorption detector. Okay, so let's think about that for a second, right? They call it indirect UV absorbance on the same capillary. They had better signal to noise in the backscatter, but less baseline stability in the backscatter detector. So let's look down here what they saw. And this relates to the article that we're looking at above, but you know, who cares? Here is the backscatter detector, 2346. These are parts per million, right? And then this is the backscatter detector. This is the ultraviolet absorption detector. And this is the refractive index detector, right? And they say that this one actually is more sensitive to the peaks, but this one has a better baseline, more baseline stability. So one of the things I'm going to have you write about in your midterm, your take-home midterm, is what's better, to have a stable baseline or a sensitive peak representation. I'm going to make a note of that right now.
Is that really more sensitive? It kind of looks similar to me.
I know, it does. It does.
All the work and you just get a tiny little increase.
Yes, I know. It's pretty disappointing, isn't it? But let's think about it a little bit more, right? They're detecting sodium ion and lithium ion. And who knows what the electronic structure of lithium plus is? Let's find that guy out. Okay, lithium plus, there's lithium. What's the atomic number of lithium? It's 3, right? Sorry, I answered my own question. Who was answering there? Was that you, Carla? Yeah, anyway, so lithium is 3, right? Lithium plus has 2 1s electrons, which is isoelectronic with what other known element?
Helium.
Yes, very good.
Chem
Excelente.
1A.
Chem 1A, exactly. All you ever needed to know. Lithium here loses 1 electron, becomes isoelectronic with helium. Now, lithium will therefore have the ultraviolet absorption of helium, but a little bit blue shifted because the electrons are bound a little bit better to the Li plus core. Okay, so does helium have an ultraviolet spectrum? Well, let's check that out. Okay. Huh. These are helium ions. Damn it. This is not what I wanted. Making a point here and you're messing me up. Stupid facts. So, ignoring what I just put up, I'm just going to assert something and we can check me out later, right? You can fact check me on this. That helium has virtually no ultraviolet absorption. I mean, eventually it does, like maybe 150, 175 nanometers, things like that. But all the UV absorption lines of helium are below 200 nanometers. That's called the vacuum ultraviolet region. And the reason it exists is because it's the region that we can't access unless we're under a friggin' vacuum. Because oxygen, nitrogen, CO2, water, silica, SiO2, they all absorb in the ultraviolet at 200 nanometers and below, right? So that's a very inconvenient set of wavelengths to use. But it also happens to be where a lot of things have ultraviolet absorption. Helium is one of them. Helium, lithium plus. What's the electronic structure of Na plus? Richard. You don't know? Take one electron away from lithium. You got Na plus is isoelectronic with neon. Right? Does that make sense to everybody? So Na plus has no ultraviolet absorption spectrum either. So basically what we're seeing in the paper here, in this is negative UV absorption peaks. What? What does a negative UV absorption peak mean? Who can tell me just on the face of it what negative UV absorption means? Positive absorption, or who can tell me what positive absorption means? Like if the absorbance of something is 0 or 1 or 2 or 3, what's happening there to the amount of light that gets through something?
It decreases.
Exactly right. Exactly right. Yes. The amount of light getting through decreases. Oops. What do we have to do to get an A every day? Oh gosh, I haven't seen this thing up to now. A lot of good, interesting things. What's Chem 55? 155. 55 is quantitative chemistry. 155 is instrumental analysis. So if you listen, you're getting an A. If you ask questions, you get an A plus, right? So positive absorption means less light gets through. Right, Richard? Absorbance of 1 means you've got 90% transmission. I'm sorry, 10% transmission. Absorption of 2 means you have 1% transmission. Absorption of 3 means you have 0.1% transmission. It's a log scale, right? Now, how about a negative absorption? What's happening there, Calvin? I can't hear you. Sorry, you're muted.
Can you guys hear
Yeah.
me?
Yes.
So it means like the light. Was that? How am I gonna say that? I'm lost. Sorry.
Okay. So who can help Calvin?
I can.
Okay, Ivy, help Calvin.
Negative UV absorption means that more light passes through the sample than passed through the reference.
Exactly. Exactly right. What did she say? Just say now, Calvin. Paraphrase what Ivy just said, please. Okay. Maybe Calvin's not going to play anymore. Damn it. So, so in this case, what they're saying is that for this negative absorption, that means that when the sodium ions or the lithium ion elutes, the solution becomes more transparent to the ultraviolet than just the buffer going, right? So whatever amount of buffer these low concentrations of ions displaces literally increases the transmission of ultraviolet light. And so that gives a negative going absorption peak. And it's kind of strange, you know? That's not how absorption is normally used or normally thought of, right? This is more like a bulk effect, you know, but that's okay. If you can see it, if it's linear with the amount of ions, et cetera, then it's useful in an analytical sense, right? Okay. How should we finish up the hour? I've got to ask you guys questions about negative absorption. And I'll have to put these papers onto the website.
Dr. Terrell, I have a question.
Yes, Dan.
Wouldn't it have been easier? They plotted the absorbance, but with UV vis, can you just switch it for the transmittance?
Well, you could. The transmittance would be positive.
Yeah, so then it would almost match the graph below. I feel like it would be much easier to see, because then you would
Right.
notice that like the transmittance increases when you add sodium, so it's
Right,
not absorbing
right.
UV anymore.
Right. Yeah, but then how could I torture you? It would be so obvious. I wouldn't be able to torture you for 15 minutes. So I don't, that I don't agree with that at all.
Fair enough. Fair enough.
Okay. I mean, the torment factor is important to me. So, yeah, you could totally do that. Just that it's just, indirect absorption is negative, So it's funny they don't. Okay, TM 350. So this is sodium. That's lithium, right? Yeah. So now what? So here, this drift in this signal. Let's assume for the moment that it's a physical property of the solution in the capillary. It might not be. It could be coming from the lock-in amplifier or something else. We don't really know for sure. But if this is something physical in the capillary, then what this is saying basically is that the refractive index has these oscillations, right? And that sodium and lithium have a higher refractive index than the buffer.
Could you please repeat that, Dr. Turo?
I don't think so. I forgot what I said. Right. If the fluctuation is physical, then it means that the refractive index of the buffer is changing with time. And what could be causing that to happen? And the answer is there are two important possibilities. Two important drivers of refractive index. One is temperature, and the other is the Carr effect, which is basically electric field. So I'm going to put that on the questions. There we go. So, so drift in the BS detector. Oh, it's a BS detector. I love it. The backscatter. Okay, all right. You guys, your BS detector should be going off now and then. The BS detector is due to temperature and refractive and electric field So it's due to changes in refractive index, which are in turn due to temperature and electric field. Okay. All right. Okay, so any questions for now? I have studiously avoided helping in any way with the homework that is due tonight or tomorrow?
Tomorrow. I
Tomorrow.
think.
Tomorrow, okay.
Tomorrow night.
So does anybody, Richard was first, Kenya was second on that. Richard and Kenya, do you have any epithets to throw out?
Just a few.
Any what?
Any insults to issue? Any complaints? Requests for tuition refund?
For the questions that it's asking about, like the Y data and the other stuff, is that specific to like definitions or what's in the graph? Or sorry, in the graph.
Shoot, I don't understand the question. Let me,
Oh.
hold on. That was, all this advising, oh my God. Oh my gosh. Oh, there it is, Raman exercise. Okay, all right. So here's the template that I was asking you guys to do, right?
Mm-hmm.
Right? You want me to do it really
Yes.
quick? Oh my God, I'm gonna do it super quick. None of you guys are gonna see, especially Calvin since he bailed. Poor guy. I don't know why I always pick on him, and then he gets upset. Okay. Cheater. Okay. Now this is Linest. We say equals Linest. We give it the Y data, which is the mixture. Then the X data, type a comma. Then we can do give it those data. And constant is false, and stats are true. And then we crack our knuckles and we do Shift Control Enter, or Shift Apple Enter if you got a Mac. And then voila, Tizolda. Then I think this is chi-squared here. But this is acetone. Toluene, EA, right? Right.
Yes.
Uncertainties, yes. And then sum is the sum of these bastards right here. Oh my gosh. And then the model acetone will equal the acetone times the acetone coefficient, but you need dollar signs on this guy. Oops. $I, $5, right? Do the same with the other guys. Anyway, you got to drag this stupid thing all the way down.
You can do all the columns at the same time, actually.
Oh my God, you probably can, right?
And then drag them all at once.
Oh my God. Okay, so you need then the, it's the, oh no, how can you do that? No.
You have to have you put a dollar
you have
sign
to-
on the 6, or I think it's on the, no,
Then
no,
you need to relabel these. Yes, you do.
It's easier if you just do the first one. After you do the first one, if you double click it, it'll just do it for you. It's a little easier that way.
But Dan, if you do it that way, if you drag it across, you're going to get ethyl acetate, toluene, acetone, right? But these are
You can plug in.
reversed.
You can plug in the first value for all three and then just drag them the three down at the same time.
Yes, you can do that. Yes, you can do that. Exactly. Okay, fine. That's enough. I'm not doing any more.
I see what happened.
Okay, cool. Good. All righty, guys.
Wait, Dr. Terrell.
Yes, Ivy.
Kenya was referring, I think it was Kenya earlier, was referring to the set of questions right under the Linest.
Oh, what is meant by
chart?
X, Y, constant, status?
Yeah, what are we referring to? Are we referring to this example specifically or like in general?
Linest. X
The
data,
Linest.
Y data, constant, stats. And then make a plot of the mixture flip and the model components. Flip. There.
So then stats is just like the definition of what it means in Excel.
Yes.
Or is it just true?
True. Stats are true. I like that one. True. That's what I meant. Okay.
Wait, seriously?
You can't say true. Now I said you can't say it, so now you can't say it. You have to give some explanation of what the statistics are. I don't know.
Okay.
Humor me a little bit. It's not a great question, but just humor me just a little bit. Okay, guys. Enough for today. I look forward to seeing you all on Tuesday of next week.
Thanks,
Bye,
Dr.
everybody.
All right, bye.
Thanks.
Bye.
Thank you.
Thank you.
Thank you.